So a little more general information about Stella. It's an acronym for Structural Thinking Experiential Learning Laboratory with Animation. And I think I was saying in the last portion of the lecture that I thought it was about 25 years ago. I guess it was 35 years ago. I know I was using it 20, 26, 27 years ago. And the purpose is that it allows you to do systems analysis even if you're lacking computer programming experience or a lot of math background. So it's a graphical programming language. It's very powerful, but it's pretty easy to learn. It's not free, unfortunately. It's about $600 educationally. It's more than $2,000 for businesses, and it can be installed on Macs and Windows. A 30-day free trial is available by ISEE Systems, and there are also student prices that are less than that $600. And we're going to be using Stella Architect. So, Stella can be a very sophisticated tool with, the ability to do many, many stocks and do quite complicated calculations. We, of course, are not going to be doing it at that level. This is the model window that, the app window that you'll be using. It's basically set up the way you'd normally set up a Windows type application. You've got your menu bar. You've got a view selector, okay? So that allows you to go back and forth between the actual modeling mode and other modes that you can use to analyze. You have the various tools, so stock, fluxes, converters, and then the little wireframe objects that allow you to connect converters to fluxes, etc. Down at the bottom, we have the run toolbar, and that's going to show you what how the model is progressing. With today's computers, these models should be running pretty quickly, so it shouldn't be a problem. Just be aware that, when you click on things, or if you call up, say, the model configuration, it's going to give you a property panel on the right. And if there are things you need to look for, we have property tabs on the bottom, which will show you different aspects of the particular selected object. So we have model view and map view. So map view is used to lay out the model diagram. Model view, you use that to complete the model equations and make your model simulate. And validity indicators will appear on incomplete variables, and in a drop-down list of errors or warnings will display on that run toolbar, as it did during the last lecture, although I ultimately decided to run it because I knew it was going to run with the errors and units that I had put in. Right. So when you find this tool, I think it's right in the middle, you'll have the choice of either the model view or the map view. And as with the last lecture, the first thing you're going to want to do is set up your model settings. How many time units you're going to run, the actual time units. So we used months, and the DT, change in time, that you're going to use. You can also select the integration method. We'll be using Euler here. These are more sophisticated and more computationally expensive approaches. Runge-Kutta-4, for instance, gives you a better solution, less prone to instability, but it does take longer to run. And then there's a larger set of settings here most of which you shouldn't use. Not for our work anyway. Again, run specs. You won't have to. You probably won't have to play with this. This allows you to calculate a DT based on the duration that you want the simulation to take, with the amount of computer power available to you. You shouldn't have to worry about that. It's going to run it's going to be able to run your simulation pretty quickly. Again, the integration method. So stocks, we've talked about this some, but I'll reiterate. They're containers of something. It's usually a quantity like a population, a carbon, amount of nitrogen, water, or energy. It's important to know what units you're measuring in. We'll be using stocks in every single exercise, so it's the most important element. And it accumulates any inflows minus any outflows. And you need to set the initial stocks, and these are then updated across time steps. Now, for instance, in the example we just had, our initial stocks were both 0. But Stella at least needs to know that. And stocks are also referred to as pools or reservoirs or state variables. Flows represent a change of quantity. As the name suggests, they flow either into or out of a stock, and sometimes both. They have bi-directional flows that some people use in some modeling. And they have a beginning and an end. The beginning is the place where the additional quantities begin to flow in, and the end is what it flows into and increases the quantity that's already there. So flows fill and drain your stocks. And flow is called a control variable. Converters, again, as I mentioned in the Zoom lecture I recorded, it's kind of a misnomer. But they're the parameters or factors that go into calculations inside flows or other converters. So values for constants, external inputs to the model. It calculates, can be used within the converter. You can put in algebraic relationships. And for example, a flow could increase the quantity of oil represented in a stock by fixed 2 million barrels per day, or it could increase it by 20 times the number of cars in the United States. Of course, you would have to use one of your little red lines to bring that number of cars in the United States into the flow. Action connectors. Action connectors transmit information, as I said, from one element to another where it can be used as a variable in an equation. So connectors indicate the immediate effect of one variable on another variable. So the converter, once created, is still unknown to a flow that might want to use that converter's value in order to make the value appear so that you can enter it into the flow's equation. You have to connect the converter to the flow using an action connector. And some people also call that an information arrow. Okay, and so once we put in a graph, we can call up the graph properties on the right-hand side just by clicking on the graph window, and then that's going to give us a series of options. Shows you where that little graph symbol is. Oh, sorry. The top red box there, that's the type of graph. So mostly you'll be using line graphs. So some flux or stock over time. You'll have an option there under that where you can put in multiple series, time series that'll be plotted. It's confusing that when you start, it says series 1, but in fact, if you click plus, you then get to define what becomes the first series. So just ignore that when you get started. And then at the bottom, you can declare the, click on the variable box, and it will give you a selection of variables that you can use. You could type in a legend, a minimum, and a maximum Y value. If you don't do that, then it's going to find a set of a range of on the y-axis that makes sense for your variable. And you can change colors and all that sort of stuff. And as you add series, you can just click on those series and add variables to your graph. Now, so if we're talking about the line graphs of some variable over time, particularly state variables, we have a couple of different kinds of state variable behaviors that we're going to discuss. Okay, so these are 6 basic shapes that describe dynamic behavior. Okay, so one type of behavior for a state would be exponential growth over time. So this is a consequence of positive feedbacks, okay? And it's one of the most pervasive and important dynamics in the environment. And so essentially, anytime you have a state that is increasing by some fraction of that state, over some time period, it has the potential for exponential growth, okay? Because you're going to have, a doubling time for that state, and depending on what the doubling time and your total time simulated, you can have variables, double and double again and double again and so on to infinity if you give it enough time in the modeling. Exponential decay, you can think of as the inverse of exponential growth. So you have some fraction of the material or energy or species that are being lost at every time interval. And from that, you can then calculate that there is some time interval where it's going to lose half of it in the next interval. And it's going to decrease to approximate 0, right? It's an asymptotic relationship to 0. That fixed interval that it takes to lose half of its value is called the half-life of the system, and you've probably heard that term being used with in relation to radioactive decay. We can also have exponential approach. So it represents exponential decay, but the system doesn't decay all the way to asymptote at 0, okay? This happens when the system receives an inflow that counteracts the effect of decay, and the system can gradually approach some kind of equilibrium. S-shaped growth resembles exponential growth in the early stages, but as the system grows larger, the amount of stuff in that particular stock grows greater, it's eventually going to encounter some kind of limitation. And those limits could be restrictions on the resources coming into the state, for instance, nutrients or breeding habitat or winter habitat, whatever it is you're modeling for population growth, for instance. For S-shaped growth to appear, the system must incorporate the effect of the limits in a way that'll gradually slow the growth and permit the system to reach an equilibrium state that can be sustained. And so the best example of that is, carrying capacity as a factor in modeling population numbers over time. Overshoot is a situation where it starts out like S-shaped growth, but the system does not achieve a smooth accommodation with limited resources. So if there are delays in the reactions to limits, the growth trend can carry the system beyond sustainable values. Overshoot can be particularly pronounced if the resources of the system are damaged during that period of intense crowding. Understanding the tendency to overshoot is critical if we're going to achieve sustainable management of human and natural systems. And finally, oscillations appear in many systems, ranging from the beating of the human heart to cycles in the economy. Some systems oscillate in a repetitive and stable manner, one that seems to ensure the longevity of the system. Other systems can enter an oscillatory pattern that's highly unstable and then threaten the sustainability of the system. This figure depicts oscillations that dampen out slowly over time, so like the damped oscillations of a pendulum. Oscillations take many forms, and they sometimes arise from delays in the system. So system modeling is a powerful way to look inside the system for an understanding of oscillations.